All right, let's dive in. Today, we're going to talk about one of the most powerful and, honestly, most popular tools in all of machine learning, the random forest. Now, I know it sounds like something straight out of a fantasy novel, right? But it's actually a brilliant algorithm that gets used for everything from spotting credit card fraud to helping doctors diagnose diseases. And really, to get a handle on this, it all boils down to one simple question. Why is a whole forest smarter than its single smartest tree? Believe it or not, that one question holds the key to this entire technique. So let's find out why. Okay, so first things first, we've got to start with the basic building block of our forest, which is just a single decision tree. You can think of it like a simple flowchart, a series of yes or no questions that eventually leads you to a final decision. It's super intuitive, but it has a really serious weakness. Now, a single tree looks great at first glance because it's so transparent. I mean, you can see exactly how it's making its choices. But here's the catch, the fatal flaw, really. It tends to overfit. It gets way, way too specific to the exact data it learned from. And, this analogy just hits the nail on the head. Overfitting is just like cramming for one specific exam. You might memorize every single answer and get a perfect score on that test, but you haven't actually learned the subject. So the second a new test with slightly different questions comes along, you're totally lost. And that is exactly what a high-variance decision tree does. It aces the old data, but fails on anything new. Right, so if one so-called expert tree is kind of unreliable, what do? How do you fix it? Well, you don't try to build one single, perfect tree. Instead, you build a whole forest of them, and then you let them vote. This whole idea has a name. It's called ensemble learning. And the core concept here is that while any one tree might be a little off or even flat out wrong, the collective wisdom of a whole bunch of different trees will actually cancel out those individual errors. It leads to a much, much more robust and accurate final answer. I mean, think about it this way, right? You would never ask just one person for their take on some really complex topic. No way. You'd get a committee together, a diverse one, with different points of view. That's exactly what a random forest is doing. It's tapping into the wisdom of the crowd. But here's the thing. For that committee to actually work, its members can't all be these carbon copies thinking the exact same way. That random part of random forest is absolutely crucial. And it's all thanks to two little secret ingredients. So how do we actually make this happen? How do we inject that randomness? Well, it really comes down to two pretty clever tricks. First, each tree only gets to see a random piece of the original data. That's a technique called bagging. And second, at every single decision point, each tree is only allowed to consider a random handful of features to make its choice. And this image here, it does a perfect job of showing that first step, which is called bagging. Take a look. You've got the original big data set on the left. We then create all these different, smaller training sets by randomly pulling data from it. And notice, it's with replacement, which just means some data points might get picked more than once, and some might not get picked at all for a particular tree. And this randomness, this is where the magic really happens. What it does is it forces every single tree to be just a little bit different, to learn slightly different patterns from the data. This de-correlates them, which is just a fancy way of saying they won't all make the same mistakes or fall into the same traps. And that is what makes the final model so much more stable and so much more accurate. All right, so now we have our forest. We've got hundreds of these slightly different decorrelated trees. But how in the world do we get one single final answer out of this whole crowd? It's actually, believe it or not, beautifully simple. So if you're trying to classify something like, is this email spam or not spam, it's just a democratic vote. Whichever answer gets the most votes from the trees wins. And if you're trying to predict a number, like, what's the price of this house going to be? We just take the average of all the predictions from every tree in the forest. Simple as that. Okay, so we've pretty much seen how random forests are this awesome solution to that big overfitting problem. They are incredibly powerful, and this is a big but, all that power comes at a cost. There's a major trade-off you have to make. So let's just quickly run through the good stuff again. First, you get a huge boost in accuracy and performance. Second, you basically solve that overfitting problem we talked about. And third, as a nice little bonus, the model can actually tell you which of your data features were the most important for making its decisions. It sounds almost too good to be true, doesn't it? So what's the catch? Why wouldn't you just use a random forest for every single problem you have?
Well, here it is. By combining hundreds, maybe thousands of trees, we lose that beautiful simplicity that we had with just one. The whole thing basically becomes what we call a black box.
See, with one lonely tree, you can follow its logic step by step. It's totally clear. But how on earth do you follow the combined average logic of, say, 500 different trees all shouting their opinions at once? The short answer is you can't. Not really. You get a fantastic answer, but you lose the ability to easily explain how the model got there.
And this brings us right back to the central dilemma, that big trade-off between performance and being able to explain things. So let me leave you with this thought. When is a powerful, highly accurate black box better than a simple, transparent answer that might be just a little less accurate? That's the key question you have to ask yourself every time you think about using a model like a random forest.